one of they wanted to come to the group. So since like when I like just before this, so we're probably going to do this paper again next week with the authors. But right now I'll just go a bit through it. So to have better questions to have read it and have better questions to ask the authors. Anyway. Anyway, if anyone has any questions or want to say something, feel free to to unmute and ask and interrupt me. Otherwise, I guess I'll just read the paper out loud and comment things that come to mind while doing that. And yeah. Spartans encoders have shown success as decomposing language model activations into a set of interpretable linear representations, latents. However, recent work identifies a challenge for Spartans encoders. High-frequency latents that are similarly uninterpretable and occur with greater than 10% of tokens. In this work, we find that high-frequency latents have many unique properties. Most high-frequency languages have a pair. Another high-frequency in the geometrically opposite direction that they never co-occur with. The high-frequency latent subspace is robust to the sparsity encoder intermediation, but the sparsity encoder, the high-frequency latent themselves are not. I'm not sure what that means exactly. Like, so do they mean that there's a space consistently? Okay, they'll explain it more later, I guess. When the sparse encoder is trading activations with the write it down as a thing to ask them later. Okay. This high frequency source. When the sparse encoder is trading activations with the high frequency latent source space ablation, no new high frequency latents are learned. And the high frequency latents have uniquely high similarity with the sparse encoder's bias vector. Our experiments lead us to hypothesize that the high frequency latent subspace is not an artifact of sparse encoder tuning, but instead represents a subspace of truly dense language model features. We present preliminary results of interpreting this dense subspace, including finding high frequency latents that represent context position, high frequency latents that fire continuously on large blocks of text, high frequency latents that fire on topic sentence, and high frequency latents that fire on numeric data. Okay, I'm curious why they are, if they figure out those things, why they are not interpretable, but we'll see. Sparse encoders and supervised learning technique defined dictionary of latents. Model activations on any token are a sparse combination of these latents. Most sparse encoder latents are monosemantic, meaning they correspond to human interpretable concepts. For instance, Temperature et al. Find a Gondel Gate Bridge latent in Cloud 3 sonnet anthropic. Okay. Which they amplify the still model behavior. That's the typical meme one. Hi. Anyway. That's anyway. If we could make a sparsity low enough to remove the high frequency latents, this might be this might be a mistake. There are dense features that language models might need to track for input tokens, such as context position. We hypothesize that high frequency latents span space of the truly dense language model features. However, sparse encoders rely on the features being sparse. Thus, in these regiments, sparse encoders must not learn high-frequency latents that align the status with the true features. Explaining why previous work have found that frequency latents are mostly interpretable. Yeah, I need to talk about this next week because this seems related to Gonzalo's thing about uh, the thing Gonzalo said the other day, and there was on a paper that we read the other day about how the the, the this compositionality problems where you can't in that view you're thinking about the sparse features, you're thinking about for example the idea of a pink element being some latent for pink and some latent for elephant. But if you have more than one object, you want to like assign the same feature to the different things, and that seems like it's related. That's uh, one, yeah, seems related in that if the model has something like this for tokens, where a lot of all of the most of the tokens have the same latent feature activating, that might be something that is important, but the model doesn't. No, in that case, I don't think you need some way of combining it with the other thing, like the ink thing, for example. But I guess you could imagine something where there is some property and all of the tokens have the same property or something. I need to think more about that. But yeah, I guess this also could be possible that you can have some feature and you're assuming that features are directions. But maybe the positional encodings are represented in some non-linear way, where you have like some vector and the longer the vector, and then you have increasingly longer vectors depending on the positional encoding or something. But I guess I will see what the paper said about the geometry of the features. Yeah, because here they say they explore the geometry and characteristics on high frequency later.
If I understood correctly from like looking at the intro again, these high frequency latents seem to be referring to the polysemantic neurons. And then when they're talking about how these are better at describing the dense spaces.
No, this is basically okay. So they train sparse encoders, and they find these in the sparse encoders there is some high frequency latents that happen in a lot of examples that don't. Yeah, that happen in a lot of examples that don't. They don't seem to be interpretable. They hypothesize here that this is not some weird book of sparse encoders, but they actually mean something, and they just happen very often. The problem is that since they happen very often, and sparse encoders are trained with sparsity rewards to be, to have only a few activations at the same time, the model is not not learning them properly. And some example might be something like there is some representation of the positional encoding, and the model is on the tokens, and the model is just not learning the positional encoding for the tokens because like the latest correspond to that because they happen always, and the sparse encoder doesn't is not incentivized. Like it doesn't like activating features all the time because it gets slower. It gets higher loss on the with the sparsity reward.
So, what they describe as, in this case, high frequency latent could be seen as a feature that, for like a neuron, it shows multiple features of one activation and it activates multiple times, but it's still interpretable. How is that possible?
It's a feature on the sparse encoder that I think on the high frequency here means that it's a feature on the sparse encoders that activates very often.
Mm.
Like that they just activates on most inputs. But I mean, if you have, I haven't, I have only started reading the paper. If not, it doesn't end up being clear. We in 2 weeks we are going to like do this paper again, but with the authors, so you can go to that one and ask them. My idea here is just I couldn't think of another paper right now to do, so I'm going to just skim through it. And then we have better questions to ask the authors, like when they come in 2 weeks. Anyway, in this section, we examine properties of high frequency latency rates. Wait, let's examine that's interpretable. And they look not interpretable, but I kind of found a way of interpreting them. Okay. Okay, and they also like whatever the high frequency latents are, there is like some negative version of the high frequency latent. I wonder maybe they'll take out more, but that also sounds to me like they might just be something like latents that are not a direction, but where the magnitude of the vector matters. And so you'll find that you sometimes have the negative version because it also has like negative values. And you, of course, you're not going to have to find that you can't have the normal activation and the negative one. I guess you can have it on different tokens or something, but I don't know. Sparse encoders latent frequency versus constant similarity. Yeah, they are so similar to the bias. I don't know what that means, but maybe they have some idea. They have some sparse encoders. High frequency lattice come in geometrically opposite pairs. I'm confused by this. Can you maybe I'm thinking about it wrong, but this doesn't seem to me like if you have two pairs of latents with consigned similarity -1, can you have them at the same time? Like it's maybe I'm thinking about it wrong, but it doesn't seem possible. Uh, like if the activations are some vector pointing in some direction, they can simultaneously be the same vector pointing to the opposite direction. Like they cancel out, right? I don't know. I'll look about it. I think about more later.
Yeah.
I'll ask
Negative opposite directions, right?
Hmm?
if it's -1 for cosine similarity, don't they have the opposite direction?
Yeah, they basically they have the opposite dimension. Here they say they do not co-occur on the same token, but I think that occurs not can co-occur on the same token, right? Because if you can have a vector on the same token, a vector and like the opposite vector, unless they mean like on different layers or something. We'll see it in table 2 later, I guess. Maybe that's better explained. Also, where are the sparse encoders? Because maybe are on the attention layers or something. They are on layer 12. Yeah, probably mean after on the typical thing after the layer norm. High frequency layers tend to be more bias aligned. Okay. So most part of encoders latent are orthogonal to the decoder bias direction. This makes more sense than I was thinking. But some of them have cosine similarity with bias. And they are the only latents with that. Okay. But there is something, some of the latents that are doing something related to the bias, basically, which they say. And the high frequency latent surface is rediscovered between sparse encoders. They are in different scenes, and their pairs. Okay, so there is some subspace that contains a lot of the high frequency latents, and the sparse encoder sometimes finds it. Like the sparse encoder is consistently find and put some. There are some sparse encoder latents that have directions on that subspace, but they don't always. Like there are. It seems like the model is maybe encoding like a lot of things on those spaces, and the model the system coders are learning to put some random directions there, but not all of them. Like not consistently the same directions, which is this is probably just an indication that sparse encoders are bad. And also something about how the way they are trained doesn't incentivize to them to learn this kind of thing well. We addressed two alternative explanations for the high frequency subspace. It's an artifact of first. It could be as an artifact of sparse encoder training, and second, it's simple the sparse encoder learning the highest variance dimension. For concern one, they do the thing where they train the sparse encoders with the same seed and ablate. They ablate these high frequency latents, ablate the subspace, the frequency latents, and then the sparse encoder just doesn't learn the high frequency latents. Okay. And consent 2 is if they are merely directions of high variance in the data, they expect the subspace, okay, which is only 10 dimensions, which is interesting. And the top PCA subspace to be extremely similar. However, the principal concern is very analysis, by the way, is what that means. However, finding the components of the high frequency latents along the top 30 PCA components, we see a significant proportion of the variance still unexplained. Makes sense. Furthermore, the high frequency latents directions themselves do not simply correspond to PCA components. Does the sparse encoder seem to be working well to break down the top PCA dimensions?
Could be. I'm not sure if I understood. So PCA is a way to find like some form of evasive vector from the vectors they give.
So the PCA is basically you find, if I remember correctly, you find the directions of the of the of the directions of the activations or whatever. It's just a statistics method in general. Find the directions of the data that have the most variance. That, like, if you take a lot of examples, the ones that are changing more, and the hypothesis here is that these high frequency latents might just be a bug of the model, like having these high frequency things that are changing a lot, because maybe there are noise or something, and putting some vector there. But if you do PCA and compare with the three high frequency latents on the sparse encoders, they don't match. So that kind of means that hypothesis is not true, probably. Okay, interpretability high frequency subspace. In this section, we investigate top high frequency latent by combined frequency. We included some initial findings in table 1 and a sample firing patterns for each high frequency latent like appendix B. Examining the latest activations at each context potential, we find that the top high frequency latent across all seeds is exactly rediscovered and has a strong context position dependence, firing mostly and strongly on early in context. Has low frequency, has a low frequency power to seeds, and no pile in the other two. In the top left, we plot the latent firing context position. Also, this seems related to another paper we did where they talk about the problems with the sparse encoders, and one of them was when the negative of the negative of some activation means something semantically related to the other activation, and you might not find a negative example on your data, so you just don't learn this negative activation thing at all. And like here, it happens that they do learn it, but yeah. Anyway, so here they're saying that they found the top latent that is consistently found by all sparse encoders they train on this, or most sparse encoders they train on this, seems to just represent the context position, depend on the position, context position. Very more strongly and early in context. Mostly early in context. I wonder if just they check if it. I'll ask them next time when they come if it goes down like consistently. Maybe it's just directly related to like has some simple geometry related to the positional encoding. Like it maybe just goes down as the positional encoding continues or something. Okay. The next two latents seems to have a meaningful firing pattern. Latent 2, also this is this on, okay, Civ 42, nice Civ. Yeah. Latent 2 fights mostly on numeric data and short common tokens, while Latent 4 fires on most other tokens. Harry, okay, so they say this is a high frequency related pair, so the one is just the negative of the other. I guess that's what they mean. It's related to semantic access similar to structured tests versus prose meaningful tokens. We observed that for some high-frequency latent files are sticky and occur in blocks. To quantify this, we found that the Markov transition matrix between states, neither fires, one fires, two fires. Okay. Yeah. Computed the state switch odds ratio, which stay on current leon, switch to pair, current leon. We observed that for certain pairs, once one latent is firing, the probability to switch to the other latent is very low. The results are shown in the top right of your thing, which specifies that these latents are context indications and indicates the property of test that persists across many tokens. As this is a paragraph about this concept. This concept refers to a certain type. Yeah, that makes sense. I mean, shouldn't they also find this for two?
Similar times doesn't mean they're a different type. How do they find that it's a paragraph or it's a type concept? They kind of.
You mean, okay, so in this case, their pairs are just the negative of one another, if I understand the question correctly.
Like, how were they able to come up with the assumption, like, or that, like, the paragraph concept and the context of a certain type, like, indicator was done when the latents, just from latents having low chance activating together?
I think the idea is that like you have something that when you have the positive latent, so I mean the thing being on different tokens. So basically, this means that you have a long sentence where all of the activations are like, for example, this paragraph is about the whatever concept latent, and you don't see on the middle any the negative that this paragraph is not about that concept or whatever that the negative means. Saying they don't show up together and they don't, not only they show up together, that they are also are likely to switch to not happening. So that means that you find, is another way of saying that, to find them together very often. But I'm not that sure of this, and you should maybe just ask the authors the next time they come.
Yeah, I probably wouldn't just consider that in the future because maybe it might be incorrect, or it could be correct.
Yeah, think about TV development, but otherwise, if you're still like in 2 weeks, if you're still not, I not that sure of this. I think I might also ask them about this, but we'll see.
Like everything else seemed to make sense, and then that part was like, I'm not sure about that.
I mean, it's not like they also know that much. Like they are also basically guessing what they mean, and just that they seem to mean something interesting, but it's not. It's super clear what they mean. And this kind of thing may also be that they also spend a lot of time looking at the text that has these latents and had a better idea, but don't didn't write out every experiment they did here. Anyway, let's look at the last one. One particular interpretable context indication is 9 and 14, which seems to indicate body text versus topic sentence. Just spawned for a moment and then disappeared. I don't know why, but let's continue.
So is it just from distance from U line, and then it's a feature in one of the transformers, or is it like every single? I guess it's in every layer.
I think they mentioned.
What did they say? Like, did they say it's just for a
No,
certain
it's layer
head,
12. This is all on layer 12.
okay, so
Like all of the
it's all
spells
layer
are on layer
12.
12.
Do they specify which head, or is it in every head?
I think it's after the attention, like on the. I don't know if after or before the MLP.
Yeah. So is it in the MLP or is it in the attention heads, or which attention?
I think if it was on the attention heads, they will say like they usually call it attention sparkle encoder. I think since they don't mention, when people don't mention, they mean, I don't remember right now if it's after the MLP or before the MLP. Like
So they
maybe
mention if it
maybe
is.
it's explained on Appendix B. I'll check it for a moment.
Okay, so but usually they mention if it's an attention attachment.
Yeah, they usually mention the attention ones because attention ones are work slightly different because you need to think about like the source and like on the if you go to Neuropedia there is some attention mental attention ones, but they have like separate activations on the soul on the different parts of the attention, and it's kind of weird. But okay, the cluster model is person. Okay, they also use K sparse encoders, which they enforce, as they said, they enforce sparsity by sharing out the activations but all the top K latent activations. So they just have, they only take they ensure that the model has sparsity by the sparse encoder has sparsity by putting all of the things at the top activating ones to 0. So the sparse encoder sense has to learn to pick the most important latents.
So it zeroes out everything that's not part of the K highest, or is it zeroes out everything that's
it's zero everything that is not the highest activations.
So it's doing like a pick K algorithm. Like
they call it a top K sparse encoder.
Is this common or is this new?
I think this is common. They've had a bunch of papers. Yeah, I know that like into sparse encoder stuff, apart from reading papers about why they don't work lately. But
I thought it was like a sparsity constant and like increasing the number.
Yeah, I think a lot of other ones just have some a other way of doing it. Just have some reward for like on the reward just have some regularization, so the model is penalized like the more activations it has, or like with the normal activations or something like that, and you took the one L1 normal whatever. But it seems they do it with top K a top K thing. But anyway, I wanted to know if where they say it. Layer 12.
Maybe it's in the appendix, like they talk about where the activations specifically.
Yeah, no, here is the appendix for the site expression encoders, and they don't say it. But I'm guessing
12,
is
activation 12. It says activation 12 a little up.
Sorry,
Yeah,
I
they
didn't
don't
hear
really
you.
define which head or like if it's in the MLP or the attention.
Yeah, but my guess is we can ask them, but my guess is just this is on the like either before the MLP or after the MLP.
Yeah,
and not on the attention.
Before or after. Have there been
I don't remember. Like there is some default thing that people use.
Yeah,
right? I don't know. It is after the
middle
rest,
and
like
end.
the. I guess
Yeah,
it
have
might be
there
just
been any cases of taking activations from inside the MLP itself? or inside the attention? Because it seems like all of them are before or after the transformer, or before and after the MLP.
I think I usually is doing after the skip connections, which I think is. I don't remember where those are on top of my head. But anyway, let's go back to the thing, and we can just ask sadly where the spurs and other activations are taken from to the outdoors next time they come here. I feel like maybe people just usually train them on the same place. And this is a dumb question, or like we should just read other spurs and other papers, but I don't remember it right now, to be honest.
At least I understood more of this paper than the previous ones.
I mean, you'll start to understand increasingly more the more papers you read.
Yeah. I think
okay. I think also like the papers we did a year ago were probably easier to understand because we like increasingly people have there is more literature and papers are citing more previous papers. And it's easier like when people like starting from when people started publishing Mech Interp papers.
Yeah. Yeah, that's how it felt.
So I understand that if you come now here, and I also, especially when the authors come, they are also assuming people already know a lot of stuff. And that's because I think a lot of the people who are come here to the reading usually already read a lot of papers. But yeah, but yeah, just keep coming until you eventually understand. Sometimes we find some easier paper, kind of depends. Anyway,
yeah, some of the papers I understood like very little, and this one, I understood the terminology. No new words.
Okay. It seems like there is not a lot more of paper. Okay, so we were here, and then there is these graphs. So there is the latents, which is like the context position, phrase level, semantic meaning, 3 context indicator, which they don't explain what the context is, but maybe it's not clear by the text. 9 and 14 body text versus big sentence. I wonder if there is like language, if there is high frequency language latents, or the language latents logo the like for if you take text, maybe that only happens on earlier layers, but if you imagine having some text that is on Spanish or French or English, there should be probably some indicator of this section of text is on Spanish.
Yeah,
and that's like it should be a high frequency latent on this context.
Yeah. Maybe like if you intentionally train a multilingual model, you could see a high frequency latent on the language they're using.
I mean, on current models, they are training on the entire internet, and they have syntax on all the models, and they can do things like translations, and they kind of have to have some indication on that. But maybe it doesn't show up if you train on layer 12, because maybe the model does language thing on earlier layers or something. Although maybe not, because it has to still know which language it is for things like translation.
Do they just manually test every layer to find these, or is it just like commonly known certain layers do these things?
I think they just pick a layer. We can ask them why they pick layer 12, but I think people usually do this kind of thing. They just pick some random layer of the video to the papers.
Okay, they just pick some random layer and then see what happens on the layer, and then
or maybe like they tried a bunch of layers and ended mentioning on the paper the one that seemed more interesting.
Ah,
and just not talk about the other ones. That can
yeah.
happen. I guess we can. That's another thing we can ask the authors, or maybe
Yeah.
they mention it somewhere on the appendix. But I do think a usual thing for this kind of sparse coder research is people just pick a layer, like that don't,
Mm.
you know, have the time to try all layers and look at all of the layers because that will be a lot more work. And even here, I think the interesting thing about this paper is more there is these high frequency layers that seem like they are meaningful, are not books of the sparse, they're books, not features, and less. We have a comprehensive explanation of all of the high frequency layers that happen on all the sparse encoders and what they mean. Because they also like point of the point that the sparse encoders seem to be missing things on these high frequency things. So they just need some better method that captures this kind of activation pattern, and then we can label all of them and figure out what they mean.
So the problem with sparse autoencoders currently probably might be the fact they can't distinguish between the high frequency latents and the polysemantic uh, latents. I don't
Yes,
know.
like the normal latent, like sparse encoders are trained for low frequency latents. For in some sense, they are they are sparse with the idea that you can decompose the text in like some token or whatever activation some text in some a small list of features that that not activate very often. And turns out that there are some features that do activate very often, and there are probably multiple of them. And the others don't seem to be don't like they sometimes capture them, but and people went understanding what they meant, but it seems they do mean something, and also they find that the sparse encoders don't consistently learn them because they train on different seeds, and some of them, like the position one, always happens apparently, but some of the other ones seem to depend on the which seed of the sparse encoder you pick. So yeah, the sparse encoders are not very good at these ones, it seems.
So there's high frequency and then low frequency. How do we interpret the normal frequency latents?
So the normal frequency latents, these ones, the other ones
Yeah, the
seem
majority.
to, a lot of them seem to be interpretable. Uh, Others don't. Like there is also, it's not just the case that the sports encoders are bad at interpreting high frequency latents. The sports encoders are bad at interpreting a lot of kinds of latents. But this is a specific kind that they found that it's that they are bad at, and that people thought were maybe just bad, but turns out they are actually meaningful. Uh,
Hmm.
at this my point that we need some different methods to
Maybe
understand.
like some tool for high frequency latent interpretability as well.
Yeah,
Maybe I'm trying to think. Maybe you make a list of all the different high frequency latents and possible low frequency latents, and then manually make code to SAE all and also graph the relationship between them.
I mean, this
Maybe.
is also like you don't have like part of the problem is we don't have the all of the like when we're talking about latest, we're talking about the sparse encoder. So we there is some there is some subspace of the direction or like around 10 directions where the model is storing a lot of important information apparently that happens on most of the tokens, and uh, we have some latents that for the sparse encoder that correspond to direction on that space that being something, but we just don't actually know how much stuff is stored there that the sparse encoders are not reading correctly. Especially could be worse because it might just not even be linearly encoded, but that's another thing. Yeah, I guess we can that we just have they just have a bunch of examples of uh, a bunch of things that they do, and then they have the conclusion. I guess I read the conclusion. Maybe we can maybe we talk about a bit more about this, and then we can just stop the recording. In this work, we argue that high-frequency latents likely represent true dense language model features, and that because sparse encoders are optimized for sparsity, it's not surprising that these features are not learned cleanly by the sparse encoders. Yeah, that's basically what I was saying. That the point of the paper is that there is this dense, dense language model features encoded somehow in a few directions that the sparse encoders are not very good at learning, and overall we believe that our work provides a way forward to understand high frequency latents. If we carefully focus on each high frequency latent one by one, they seem feasible to interpret. We also can try rotating the high frequency latent space to result in maximal interpretable latents by some metric. As we hypothesize that the high frequency latents of space current orientation might not line up with the model's ontology. I mean, isn't that like all sparse encoder? I mean, that's kind of what the softwares are trying to do, but I guess they mean some other method. But yeah, again, it might also be that that subspace also has some things that are not represented linearly or with some geometry that matters. Or like example of how it could not be linear. You could have the different lengths of the directions mean something. And you can then separate that with ReLUs. And that is something that the model can just not do. Like the sparse encoders can't figure out. Because it will be like, for example, if you are representing the position by having like the same, in some sense, the same vector but longer or shorter depending on where the model is, that's not going to show up on the. I have like if I remember, not exactly that, but there is something vaguely like that on the Grokking paper, because in that case it's a bunch of vectors that you need to put on the Fourier spaces to figure out. But yeah, the positional encodings there not the positional encodings there is just the numbers, but the numbers are just represented on the same space. Like some activations that don't look meaningful for each number. But when you have all of the numbers together, you can see them going up and down depending on the numbers. And if you plot that on the Fourier space, you get some nice sine function. And that sparse encoders won't tell you that kind of thing at all. And maybe we need something else that isn't sparse encoders to do interpretability, but I don't think people have figured that out yet. And this paper seems a nice. This is a example of a specific thing that sparse encoders seem to be missing, and that if we need to come up with some alternative to sparse encoders, it's something we need it to do, like to deal with these frequency things that happen on the model, this dense feature that happen on the model.
So the things they're missing is clearly the high frequency latents and also the inability to capture the nonlinear transformation.
Yeah, there's probably more things that we just haven't thought of. That so there will be some other paper that says, okay, so the sparse encoders can't figure whatever this other thing is, and then we also need to do that. But yeah, that's the one that comes to my mind. Yeah.
So maybe have there been any attempts to capture nonlinear activations and make them interpretable?
I think there are problems with that. There's probably some, but I think there are problems with that. If you start doing complicated nonlinear things, the method is less nice, and also it becomes Yeah, I'm not sure. I think there is a problem. This is more in prose, but there is a problem of how much the classification you have on the your complicated nonlinear thing is actually part of the model or just some new thing that your nonlinear sports encoder thing has made up. Uh,
It's hard to tell if it's noise or actually in the actual.
Or like, for example, imagine that you have. I mean, I'm not sure if this makes sense, but the thing that I can imagine, if you imagine some model that doesn't understand what English is, that does some text in English and some text in Spanish, and or maybe yeah, and you could imagine that maybe there is a super complicated mess of latents that all mean some subcomponent of that altogether just mean that the model is that sometimes it's in English and the model just doesn't have an English feature but it has some terrible mess of features that combine with each other. Maybe your complicated non-linear response to encoder thing learns to summarize that with an English feature. The model itself doesn't, but I don't think that will be that bad of a problem. If you have some abstract generalizations on top of that, yeah, okay, that doesn't, it's not that much of a problem. I guess another thing is with the linear things is that it's just harder to make it work correctly. And I guess it's not non-trivial to make some non-linear version of that code that works. But I'm not sure people have tried that much. There is probably some other like theoretical reasons why it doesn't work, but if you come up with some idea, maybe you should just try and see what happens. Because not like people have tried that much. Like Sports Coders was like the simplest obvious idea, and maybe we just need some. There is some dumb thing where you add some non-linearity to it and it just works, or it works better at least, and people haven't just thought of it.
Yeah, that's an interesting. Like, I never learned about some of these, so that's cool.
Mm. Like at least improves is usually a valid idea, but and I was thinking having that thoughts about that, but like like improves using non-linear feature is a bad idea because you want to figure out how the model is encoding the thing, and your probe by just be able to like maybe you want to figure out if the model has some information in some position and the model is not calculating that at all and instead your probe is doing the calculation, but I don't think that's net obvious. I will need to think more about whether that's a problem in sparse encoders though. But yeah, anyway, I think unless you have any specific questions, I'm not going to go through that much about all of the appendices. I think we can just leave it here, and we can we'll go back to this paper in 2 weeks when Josh Engels and the other author, I don't remember the name, come here. And now that at least I have read the paper, I can have like better questions to ask them. Like maybe where the sparse encoders, where the sparse encoders are,
Yeah.
which part of the model are trained. That one might just is probably better. I should just read what the other or check Neuronpedia and see where those are trained because it's probably everyone is training on in some default position. I just forgot it right now. Maybe that it's a dumb question, but. Apart from that, yeah, I think it's okay now. And yeah, we can leave it here.
Okay, so I will be stopping the recording.